Have you ever walked into a room and just felt something was different about the sound? Well, today, we're going to dive into that hidden world of acoustics. It's like an invisible architecture that shapes everything we hear. I mean, really think about it. You walk into a huge cathedral, and your voice gets wrapped up in this rich, almost magical wash of sound. But then you step into an empty gym, clap your hands, and all you get is this messy, rattling, chaotic noise. What's the deal?
Well, the secret isn't about what the rooms look like, it's about how they sound. The room on the left, that's an acoustic nightmare. Every single sound just bounces wildly off those hard surfaces. But the room on the right, now that's a space that's been carefully designed to sound good, using simple stuff to tame all that chaos. You see, the sound of a room is almost always a deliberate choice.
And that's really what this is all about. The entire personality of a space, whether it's a huge concert hall or your bedroom, it's all defined by how sound waves reflect off the walls, the ceiling, and the floor. Okay, so let's start by breaking down the two words you hear all the time when you talk about this stuff: echo and reverberation. Now here's the part that might just blow your mind. Echo and reverb, they're basically the exact same thing. Yep. They're both just sound waves bouncing around. The only difference is how our brains decide to interpret them. It's not a physics thing, it's a brain thing. So an echo is what you get when you can hear separate, distinct copies of a sound. You shout hello into a canyon and you hear back hello, hello. But reverberation or reverb, that's what happens when there are so many reflections and they're so close together that they all just blur into one single continuous tail of sound. That's the cathedral sound. This visualizes it perfectly. An echo is like a series of individual pings. Reverberation is a smooth, continuous decay. The key difference that separates them is just one thing: time. But what's the magic number that turns one into the other? It's this: 60 milliseconds. That's 61 thousandths of a second. It sounds impossibly fast, right? But to our ears, that tiny slice of time changes everything. You see, it all comes down to a neat little trick our brain does called integration time. Think of your brain as a super fast sound editor. If a reflection hits your ear within about 60 milliseconds of the original sound, your brain just stitches them together and says that's all one sound. It just sounds richer. But if that reflection arrives just a little bit late after the 60 millisecond deadline, your brain flags it as a totally separate event. And that is an echo. Now, one of the most annoying examples of this is something called flutter echo. You've totally heard this before. You're in an empty hallway or a concrete stairwell, you clap your hands, and you hear that weird, zinging, metallic sound. That's just a single sound wave getting trapped, bouncing back and forth between two parallel walls. So how do we stop that from happening? So how do we get a handle on all these wild reflections? Well, we can't really stop sound from bouncing, but what we can do is control how much energy it loses every time it does. And that is the power of absorption. It's really just a simple exchange of energy. When a sound wave smacks into a surface, some of that energy bounces right back into the room. But the rest of it gets soaked up by the material itself, and it actually turns into a teeny tiny amount of heat. The more sound you can get absorbed, the less you have bouncing around causing trouble. And of course, scientists have a way to measure this. It's called the absorption coefficient. It's just a super simple rating on a scale from 0 to 1. A material with a coefficient of 0 reflects pretty much all sound, while a material with a 1 absorbs it all. You can just think of it as an acoustic sponge rating. And it's pretty much exactly what you'd guess. Hard, dense things like concrete and glass, they're really reflective, so they have a very low absorption rating. But soft, porous materials like a heavy carpet or thick curtains, they're super absorptive. They have a high rating. This is exactly why throwing a rug down on a hardwood floor instantly makes the whole room sound quieter and less echoey. Okay, so now that we've got the basics down, let's check out the really cool part: how the pros use all this knowledge. You see, architects and acousticians don't just fix bad-sounding rooms. They actually design rooms to sound amazing from the very beginning. They're literally sonic architects. But to do that, they need a target to aim for, right? They need a standard way to measure and describe how live or dead a room sounds. How long does the sound actually stick around? The industry standard for this is called reverberation time, or T60 for short. It's simply the time measured in seconds that it takes for a loud sound in a room to fade away by 60 decibels, which is basically from loud to silent. A long T60 means you have a very live, reverberant room. A short T60 means you've got an acoustically dead one. And figuring out the T60 really just comes down to a simple balancing act. On one hand, the bigger a room is, the more volume it has, the longer it's going to take for the sound to fade out. But on the other hand, the more absorptive stuff you put in that room, the faster the sound dies away and the shorter the T60 gets. And here's the crucial thing. There is no single perfect reverberation time. It's all about matching the sound of the room to its purpose. For a lecture hall where you need to understand every single word, you want a really short reverb time for clarity. But for a concert hall where you're listening to a symphony orchestra, oh, you want that long, lush, beautiful reverb to make the music sound epic. So, with all of this in mind, you're now basically equipped with a new way to experience the world. You have an acoustic superpower. We can go all the way back to the start and look at those two rooms again, but now we understand exactly what's going on. We're not just looking at a bare room versus a furnished one. No, what we're really seeing is a journey from total acoustic chaos to engineered, controlled clarity. And that's really the main takeaway here. The sound of a space is just as much a part of its design as the walls and the windows. It is, quite literally, architecture for your ears. So from now on, when you walk into a new space, your office, a restaurant, a quiet library, just stop for a second. Close your eyes and just listen. Is the sound clear or is it muddy? Can you hear distinct echoes or just a soft wash of reverb? The next time you walk into a room, what are its walls going to tell you?